Hello all, today in this video lecture I am going to explain the wrapping effect of the bilinear transformation method. So one thing I want to remind you is bilinear transformation is suffering from the wrapping effect. So we will see the wrapping effect, wrapping effect. So what is meant by wrapping effect here? See, this wrapping effect we are going to encounter it in the bilinear transformation method. As we all know that bilinear transformation method is a conversion of analog filter into the digital filter, right? So if you are converting a filter from the analog to the digital domain, there will be non-linearity between in the frequency axis. That nonlinear distortion is nothing but the wrapping effect. So this point I have mentioned here, it is the nonlinear distortion of the frequency axis occurring when the mapping of analog filter into the digital filter. See, this wrapping effect occurs in the bilinear transformation method, right? So the bilinear transformation method is converting the analog filter into the digital filter. It means that you are mapping the frequencies from analog domain to the digital domain. So whenever you are mapping that, so that the nonlinearity or the distortion occurs is called as the wrapping effect. So to explain that concept, we will see the relationship between the angular frequency and the digital frequency. As you are converting the analog domain into the digital domain, so it means that you are converting the angular frequencies into the digital frequencies. Generally angular frequencies are indicated with the omega, this omega, and the digital frequencies are indicated with this omega. So the relation between the angular frequency and the digital frequency we are indicating is as a omega is equal to 2 by t into tan of omega by 2. Okay, next, and omega is equal to 2 tan inverse of omega into t by 2. This is the formula. Okay, so for explaining this concept we will take the help of the mathematical values. See here, for small values of omega, it means that for small values of omega I am taking tan omega is equal to omega only. So because see here, so this analogy I have taken from the mathematics. For small values of theta, tan theta is equal to theta, right? So in place of theta you have omega by 2. So for small values of omega, the tan omega by 2 will be equal to the omega by 2. So omega is equal to 2 by t into omega by 2. 2 will get cancelled. So omega is equal to this omega by t, or omega is equal to angular frequency omega into t. So here see, for small, so this relationship is possible when you take the small values of omega. What is this relationship gives you is the digital frequency is in linear with the analog frequency, even in the conversion also. Okay, so for low frequencies the relationship between the omega and the angular frequency omega and the digital omega are linear, so there is no disturbance in the filter response. But for in case of high, see, that will be drawn like this. For low frequencies, when omega is equal to omega t, so with the black pen I have drawn here, this is the response. But as you are increasing the frequency, so the response is not linear, so it is deviating like this. I have indicated this with the red color. So this is deviating, right? So this deviation gives you the distortion in the amplitude. See, this is the amplitude, this is the h of e power j omega, and this is the omega value. So whatever the changes in the nonlinearity, it is giving the bigger distortions in the amplitude. So it means that what I can conclude is wrapping effect is nothing but at the low frequencies the conversion is similar. Okay, the conversion is easy and the angular frequencies are also equal to the digital frequencies. But if you increase the frequencies, the angular frequencies will not be converting into the digital frequency, even though they are converting, so there is a distortions. So this is the wrapping effect. So to avoid this wrapping effect, we are going for the pre-wrapping of the filters before designing that. So pre-wrapping, this is the pre-wrapping effect. The wrapping effect can be eliminated by pre-wrapping the analog filters. This can be found by pre-wrapping the analog frequencies using the formula omega is equal to 2 by t into tan of omega by 2. It means that whatever the frequencies, passband frequencies and stopband frequencies, you are going to pre-wrap it. So okay, so this can be explained by using an example. So let us see the example here. See here. So using the bilinear transform transform, design the high pass filter which is in monotonic passband with a cutoff frequency of 1000 Hz and down 10 dB at 350 Hz, and the sampling frequency is 5000 Hz. So this is the frequency they have given. So in this point, the clue point they have given is bilinear transform. So bilinear transform means using the bilinear transform, he is asking you to design the high pass filter. So this is one more key point you have to observe. So here they are not asking you the low pass filter, they are asking for you the high pass filter. And monotonic in passband, this is also one of the clues. The filter which is having monotonic in passband is nothing but the Butterworth filter. Okay, so whereas Chebyshev filter is not monotonic in the passband, so they are having the ripples. Okay, monotonic in passband means this is a Chebyshev Butterworth filter, and he is asking the design of the high pass filter, and using the bilinear transform he has given. It means that you have to pre-wrap the frequencies before designing. Okay, let us write the data here. So alpha p is equal to 3 dB, monotonic in passband has given means 3 dB cutoff frequency. Alpha p is equal to 3 dB, alpha s is equal to 10 dB, he has given 10 dB here. Down 10 dB means alpha is equal to 10 dB here, and omega c which is equal to omega p is equal to 1000 Hz he has given. So, and I told you if the frequencies have been given in the hertzes, you have to convert that into the radians per second. I have told this in the previous video lectures also. To convert the hertzes to the radians per second, simply multiply 1000 with the 2 pi. So 2 pi into 1000 Hz, it is equal to 2000 pi radians per second. Similarly, we have did for the omega s also. And the sampling frequency has given 5000 Hz. So to convert that into sampling rate, t is equal to 1 by f. So 1 by 5000 gives you the 2 into 10 power 4 seconds. Now I told you now the characteristics are the monotonic in passband, so the filter is Butterworth filter. This point we have discussed already. Now before designing that, we have to pre-wrap the frequencies. How to know that we have to pre-wrap the frequencies? Because in the problem itself they have given you that bilinear transform. Whenever you are designing the filter with the bilinear transformation, it suffers from the wrapping effect. To avoid that, we have to pre-wrap it. Okay, so first we are pre-wrapping the frequencies. So omega is equal to tan 2 by passband frequency, omega p is equal to 2 by t into tan omega p into t by 2. So 2 by t is nothing but 2 by t is nothing but 2 in 10 power 4 tan omega p is the frequency has given 2000 per radians per second, into t is equal to 2 into 10 power 4 by 2. So I have done this using the calculators. I got 7265 radians per second. Similarly, I have did for the omega s also. So omega s I got is equal to 2235 radians per second. See the questions, you can note it. Omega s is equal to 2 by t into tan omega s by 2. So same calculation I did. So 2235 radians per second. So whatever the omega p, omega s are the values for the high pass filter, because they given the high pass filter. So there might be the values are for the high pass filter only. But we have learned the designing procedure for the low pass filter. So we know that the high pass filter passband frequency is equal to the low pass filter stop band frequency. So that's why omega p of the high pass filter is the omega s of the low pass filter. So omega s of the high pass filter is the omega p of the low pass filter. In the similar way, see, we design the low pass filter, we use the suitable transformation to obtain the transfer function of the high pass filter. Okay, first of all we will design the low pass filter. So low pass filter n is equal to log of 10 power, this formula you know, under root 10 power 0.1 into alpha s minus 1 by 10 power 0.1 into alpha p minus 1 by whole divided by log of omega s by omega p. Omega s is equal to 7265 radians per second, omega p is equal to 2235 radians per second. Once again I am telling you, here omega p is the passband frequency of the low pass filter, which is nothing but the stop band frequency of the high pass filter. That's why I have substituted like this. So if you do like that, you got the n is equal to 1. So the order is equal to 1 we get. So Butterworth filter of order 1, the transfer function is equal to 1 by s plus 1. Okay, so this is the h of s of the low pass filter for omega c is equal to 1 radians per second, but actually the omega c, which is equal to omega p of the high pass filter, is equal to 7.65 radians per second, and we have designed this for the high pass filter. To convert that into the low pass filter, to convert that into the high pass filter, you have to substitute in place of s by omega c by s. This is the key point. You have to remember, until unless this is the transfer function of the low pass filter only. We didn't design the high pass filter transfer function. So after substituting this s as omega c by s, we have converted the s into low pass filter into the high pass filter. So I am substituting in place of s as 7265 by s. 7265 by s, simply I have taken the LCM. So after this denominator will go into the upward direction, so s by 7265 plus yes. So I got h of s is equal to 7265 plus yes. So now this is the transfer function of the high pass filter. So but we have obtained the high pass filter transfer function, but this is in the analog domain only. But the question they are asking us to design the digital filter, and to convert the analog filter into the digital filter, they are asking us to use the bilinear transformation method. So after bilinear transformation method means, in place of yes, we have to substitute 2 by t into 1 minus z inverse by 1 plus z inverse, right? See, now using the bilinear transformation method, h of z is equal to h of s when you substitute s is equal to 2 by t into 1 minus z inverse by 1 plus z inverse. So whatever the h of s I got, in that h of s I am substituting this value. You can note down these values and you can do the mathematical simplification. See, s means yes, this is yes. In place of this yes, I have substituted this plus 7265. Now do the mathematical simplification, and this 2 get cancelled, this 2 will get cancelled. 1 by 10 power 4 minus 4 means 10,000. So I have substituted. So finally I got h of z is equal to 0.5792 into 1 minus z inverse by 1 minus 0.1584 into z power minus 1. This is the final answer. So so this is the winding of the bilinear transformation methods. Thank you. In the next video, I am going to explain you the realization of the filters, especially IIR filters. So for more interesting these concepts, you can come and subscribe my videos. Thank you.